Hi students. In this lecture, I am going to discuss previous year's IIT questions. Let us see first one. See the question given. A wedge of mass m and triangular cross section AB equal to BC, that is equal to R, is moving with a constant velocity minus V I cap towards a sphere of radius R fixed on a smooth horizontal table as shown in figure. The wedge makes an elastic collision with the fixed sphere and returns along the same path without any rotation. Neglect all friction and suppose that the wedge remains in contact with the sphere for a very short time, delta t, during which the sphere exerts a constant force F on the wedge. Asked for 8 marks in 1998. So we have to calculate the force F and also the normal force N exerted by the table on the wedge during the time delta t. Let h denote the perpendicular distance between the center of mass of the wedge and the line of action of F. Find the magnitude of the torque due to the normal force N about center of the wedge during the interval delta t. Let's see a diagram once. Wedge moving left side means along negative x-axis. That's why minus vi cap and speed is now fixed. And a condition given that it is elastic collision. Okay. And returns along the same path without any rotation. So its meaning is it has only translatory motion, right? Wedge is having only translatory motion before and after, right? Let us see how to start the problem. Right. First of all, we have to calculate the force acting, right? Force F and also normal force by that table on the wedge. Right. First of all, make a diagram, that given diagram. This is now sphere. And a wedge is moving. The wedge is moving towards it. And given that it is x and this is z. So y is into the board plane. Its velocity v minus I cap direction left side. It is v. And collision given elastic. That means for elastic collision, u value is 1. Okay. And we are given time of contact delta t. Now see what happens. Let us make a diagram once again. When wedge comes in contact with the sphere, force will be normal to the surface. It is normal to surface. You can see here when wedge is in contact, Right, when wedge is in contact with the sphere, force will be normal to that surface. It is like this, that is F. Okay. And let us say this is now centroid. Okay. Now see what happens. Condition given that it is elastic collision. Therefore, velocity of approach and velocity of separation both having same magnitudes. That means change in momentum will be 2mv. Okay. And this is equal to, you see, force component along x-axis. Force component along x-axis will be, let us take here a horizontal line, means along x-axis. This is now fx. See, this is now 60. This also 60. Okay. That means now this angle is 30. Okay. This is f cos 30. This is f cos 30. Then change in momentum along x-axis is equal to f cos 30 into delta t. Okay. So net force into delta t. See what we are doing here. Net force is equal to dp bar by dt. Okay. So net force into dt, the time interval gives a change in momentum. Okay. So from this we are going to get f value. See how much f value from here. I'm writing here f cos 30. Cos 30 root 3 by 2. That means f equal to root 3 by 2. It is 4 mv by root 3 delta t. Right. So cross check once. So we have taken that f cos 30. This is the force acting on the wedge. That force into delta t. This gives us change in momentum along x-axis. Right. So from that f equal to 4 mv upon root 3 delta t. Okay. Right. Let's see what we can do. It's asking force, right? Force on this wedge. So if you want to take now in vector form, that will be, we got f cos 30 I cap. Remaining is now f sin 30. So I'm writing here f bar is equal to f cos 30 I cap. You can see here f cos 30 along positive x-axis and f sin 30 along negative z-axis. So I'm taking here minus f sin 30 k cap. Okay. So see what we got here. This is root 3 by 2. This is 1 by 2. So I'm taking 1 by 2 outside. So this becomes now 2mv upon root 3 delta t. Remaining is now root 3 I cap minus k cap. Okay. So if you want modulus value, that is 4mv by root 3 delta t modulus value. So this is now in vector. Okay. Next we can see. So we have to find in that. See the next question. What we have to calculate. Asking normal force exerted by the table on the wedge. Right. Coming to on the wedge. On the wedge, you can see forces along vertical, normal reaction from ground, normal reaction from ground, that is vertically up, normal reaction from ground. Next, this force component is downwards. It is downwards, that is Fz can along the axis downwards. Next, mg downwards plus mg. And this Fz is how much we got? F sin 30, right? That means F sin 30 plus mg. That is now equal to normal reaction from ground on the wedge, because wedge has no motion along vertical, right? Now focus here. What else we have to calculate? Okay, first part over. Coming to second part. Let H denote the perpendicular distance between the center of mass of the wedge and line of action of F. Find the magnitude of the torque due to the normal force N about center of the wedge during the interval delta t. Now focus carefully. In this diagram, we can see the force F by the sphere on the wedge is now like this. Okay, so I'm making diagram once again here. And force F that is now passing. Suppose this is now centroid. Okay, and that force is now, let us say, by the sphere, that force is now like this, normal to the surface like this. This is F. Now condition given that H denote the perpendicular distance between the center of mass of the wedge and line of action of that force. That means if we draw normal from centroid to the line of action, this is normal, this length equal to H. Okay. Now we have to find torque due to normal reaction. Now you can see about center of mass, because of this force, torque will be anti-clockwise. But condition given that it moves back without any rotation. That means net torque about center of mass should be zero. Okay. So when we are taking net torque about center of mass, because of gravity, no torque. Because of this force, torque is now anti-clockwise. So now there must be some other torque which is balancing this torque. And only possibility is now, that is normal reaction due to ground on the wedge. Okay. That means this is not passing through center of mass. Okay. That is now maybe somewhere here. Okay. This is now normal reaction from ground. That means normal reaction from ground on the wedge plus torque due to that force totally equal to 0. Means modulus values must be same. Okay. Directions opposite. Means this is now by applied force about center of mass anti-clockwise. Then by this it must be clockwise. So torque due to normal reaction from ground, that is equal to F into H. Okay. And we know what is F. Okay? 4 mv by root 3 delta H. That is F value. So substitute here 4 mv upon root 3 delta T into H. Okay. Suppose in this question, if they ask by what distance normal reaction has shifted. Okay. So when there was no force on the wedge, normal reaction it was passing through centroid. Okay. So now here it has shifted by some distance. Suppose that distance take it as x. Then this must be equal to normal reaction from ground into x, where x is by what distance normal reaction has shifted. Okay. Then we get that distance. Okay. Let us see next problem. Right. See the question. Two heavy metallic plates are joined together at 90 degrees to each other. A laminar sheet of mass 30 kg is hinged at the line AB joining the two heavy metallic plates. The hinges are frictionless. The moment of inertia of the laminar sheet about an axis parallel to AB and passing through the center of mass is 1.2 kg meter square. We can see diagram here. Two rubber obstacles P and Q are fixed. You can see one on each metallic plate at a distance 0.5 meter from the line AB. This distance is chosen so that the reaction due to the hinges on the laminar sheet is zero during the impact. Initially, the laminar sheet hits one of the obstacles with an angular velocity 1 radian per second and turns back. If the impulse on the sheet due to each obstacle is 6 Newton second, find location of center of mass of the laminar sheet from EB. At what angular velocity does the laminar sheet come back after the first impact? After how many impacts does the laminar sheet come to rest? So asked for 10 marks in 2001. Let us see how to start. First, focus your diagram. This is now one laminar sheet. This is now rotating about AB. Makes collisions with the rubber sheet, rubber obstacle, and moves back. Okay. You can see this is just like giving an impulse to this laminar sheet at some distance so that hinge reaction will be zero, right? Almost same kind of problem. Right. Let us see how we are solving it. Well, so if you remember, while discussing hinge reaction, we discussed one problem. A rod fixed. Imagine there is a rod in a horizontal plane whose one end is fixed. Now, at what distance from the fixed end, impulse should be given so that hinge reaction will be zero or force applied. Okay, hinge reaction is zero. And we got answer 2L by X, right? Now, almost same kind of question. This is now laminar shape. Okay, and say at what distance impulse is given? It is given now at a distance 0.5 meter by those rubber obstacles. Impulse is given on the sheet at a distance. This is, you can take that this is AB at a distance 0.5 meter and impulse is given. Now you can see impulse how much is given. So impulse At angle 90, I value first right here. I value about center of mass. That is now 1.2 kg meter square. Next, mass of the laminar sheet 30 kg. 30 kg. Next, that gives impulse. See how much given impulse? Initially, angular velocity. Let us call it as omega naught initial value. That is given 1 radian per second. 1 radian per second. And next, see what else given here. See anywhere impulse is yes. Impulse, right? Impulse on the sheet due to each obstacle. Impulse that is given as 6 newtons. This is now given data. Now see what we are doing. Impulse. This is now net impulse, which is equal to change in momentum. That is m into see velocity how much initially this distance. Suppose it take it as so this is now given 0.5. Okay. So now what we are doing here is we are focusing now center of mass. So when we are writing momentum equation or change in momentum, we are focusing for center of mass. Okay. Suppose center of mass is at a distance x from AB. Okay. Distance equal to how much? It is x. Then velocity of center of mass before collision 1 into x. After collision, if velocity that is now x into omega, that means the laminar sheet turns back with an angular velocity omega, which we have to calculate. Okay. First of all, we are writing impulse. This is now net impulse. The reason is that there is no hinge reaction from the support that is given. That's why this becomes net impulse. Net impulse equal to change in momentum. So we are taking momentum for center of mass. Okay, velocity 1 into x. Next, omega into x. So before collision, after collision, direction of velocity of center of mass is reversed. That's why we have taken plus here. Next. So this is now how much? 6. Here 5 times. That means x into 1 plus omega that is equal to 1 by 5. Okay. So take it as equation 1. See the next equation, what we can write here. It is angular impulse. About this axis, angular impulse is j into j value 6, j into 0.5. At what distance this is acting? 0.5. Angular impulse that is equal to I into omega. And we are taking I value about AB, right? Because rotation is now about this axis. So IAB into omega. And while taking omega, change initial value 1, final value omega. Direction is now, if initially clockwise, finally anti-clockwise. So it is now omega plus 1, right? Now in the place of IAB, see what we have tried. IAB is equal to ICM plus m into x square, distance of center of mass from AB. Okay. Now see here. Coming to calculation part, substitute this in this one. 6 into half, it is 3. So 3 equal to ICM, that is 1.2 plus 30x square into, in the place of 1 plus omega, I am writing here 1 plus omega 1 by 5x. 1 by 5x. Now, this equation completely in terms of x. Now, simplify this. 30x square plus 1.2 minus 15x, that is equal to 0. Now, if you solve for x, so we are going to get now two values for x. One is 0.1 meter, second one 0.4 meter. Now in this, for 0.4 meter, omega comes out to be negative. Okay, it comes out to be negative. That's why this is not taken, because omega cannot be negative, because this is a modulus value. Okay, that means x value is now 0.1 meter, right? So after having this 0.1 meter, let me take in this one, then see what we get. 0.1 from 1. 1 plus omega equal to 0.1 means 1 by 10, right? 1 by 10. So 2 times, that means this is equal to 2, right? That implies omega value 1 radian per second. Okay, that is omega value. And you can see here, before collision omega value 1, now also omega value is 1. That means now this makes collisions continuously. Okay. So first question, find location of center of mass of the laminar sheet from AB. That we got how much? 0.1. Next omega value, that we got 1 radian per second. So initially 1, now also 1 only. That means this continues. Is asking after how many impacts. There is no limit for this. This will continue. Means infinite number of impacts it will make. Okay.